build bash, there's the .in file. You can change the name. That's just a text. And then there's the header file. You probably will need to modify, but you'll need to get the right one for your setup. Like the old upwelling.h, you'll sort of need to have. And that's when you download ROMs, it's in it's part of the package. So yeah, I would say you probably would need to, at minimum, modify just modify the compilers. You got to modify the build.bash. You got to modify that .in file. But at a first cut, I would strongly recommend viewing this online video where this guy starts from scratch, downloads ROMs, and compiles this upwelling case. And if you just mimic that, it's at least gets you started on the upwelling case. So it kind of shows you which folders to change. I can show you too, but at this point, I don't know how much it helps to be really specific and give you line-by-line instructions sort of to a big group, as opposed to just answering sort of broad general questions. Yeah.
Are you familiar with how the tiles work? I mean, is that related to the differential equation?
The tiles, they're not really related to the differential equation. The tiling is a way of telling the MPI how to parse out pieces of the code. And the tiling there are these halo cells that you need because at the edge of each tile you need to compute derivatives, say. To compute derivatives using finite differences, you need a couple points on that side, a couple points on this side. So there are extra cells that spill over that overlap from one tile to another. So you basically, like if you want, say, 16 processors, I know that I can divide it up into 4x4 cells or 2x8 cells, that kind of a thing. So the number of tiles has to equal the number of MPI processors on the question. But other than that, it's not really connected to the differential equations.
How does the haloing, how big the haloing area, the portion of haloing cells compared to the area is it?
I believe the haloing are like 2 or 3 or 4 cells. Period.
4 cells?
So it's, I don't even think it's 4 cells. It's 2 or 3 cells max. And so optimal tiling is where the number of tiles on the inside is large as compared to 2. So if you chop it up and in the end you just have 2 cells inside or 1, at that point you're really inefficient. That's my idea of the rule of thumb, that 2 or 3 cells that spill over. So you want the number of cells on inside of each tile to be large as compared to 2 cells. I'm not sure. So hold on a second.
Okay.
You have more tiles than machines?
On Ravel, I make the number of tiles exactly equal to the number of machines, well, number of processors requested. So in each machine has 4 processors. So I've set it up so that if I'm requesting 8 machines, I make sure I tile up to 32 tiles.
What's the difference between the 2D and the 3D model?
The 2D model integrates forward in time the depth integrated equations of motion. So all that really does is solve for how the sea surface height evolves in time. There we are. So, does it have? I wonder if it's got an actual equation. Well, it's okay. What happens if you take the equation of motion? These are all 3-dimensional, so this equation holds, at every x, y, and z location. But if you depth integrate this, you lose some terms. But more importantly, you're just evolving the depth integral, so the total velocity flux, the total volume flux. So instead of having a 3-dimensional equation, you just have a 2-dimensional equation, and if you so there's fewer grid points to keep track of. I don't know, does that answer your question?
So can you only simulate 2D without the 3D part?
You can, actually. And there's 2 ways to do a 2D simulation. You can do like a simulation where you look from above. So like if we have like Avila Beach, and I suppose I have my grid out here, and, you know, I have my grid through like that. I can have it run in a mode where I pretend there's no variation with depth, so that all that happens is the sea surface comes up and down, there are waves, and there's a velocity. And like I showed at the animation of that one velocity, and we didn't see any, in that animation, any dependence on depth. But underneath that, their velocities down below were different than the velocity at the surface. And so, but you can do a run where you neglect that. Things run much faster. It's called some shallow water modeling, where you assume that the velocity and the temperature and the salinity don't depend with depth, or depend on depth. So you can do, that's one kind of thing. Another way of doing it is assume the coastline of California is perfectly straight, so that at any cross section, you get exactly the same stuff going on. And then what you do is you just say, well, now let's look at that cross section. So here's the sea surface, and here's the bottom topography. There's a continental shelf break. So there's another version of two-dimensional modeling where you have flow into and out of the page, and so you have your sea surface height, and you can tee up. I've done bronze runs like this too, and this is where you can kind of change this bottom topography, make it steeper or shallower. Look what happens when you have a shelf break or no shelf break, and see how the water, like upwelling is this classic thing where the water moves offshore and this water moves up from below. So yeah, it's this really flexible system so that it's teed up so that scientists can do science sort of on this little laboratory